Hello everyone. In the last two videos of this series, we established several important results. We call these results hidden assumptions because they are often given too little attention in introductory solutions. These hidden assumptions are critical to understanding the derivation of solutions for the acceleration of the masses and for the tension. These omissions, while done with good intentions to avoid advanced material not yet covered in class or text, often leave novice learners confused. So, these are the hidden assumptions and their implications for the ideal Atwood's machine. 1. The implication of an inextensible string is that the masses accelerate at the same rate. That is, the magnitude of A1, which is the acceleration of mass 1, equals the acceleration of mass 2. As a result, we can replace these generalized accelerations in our system of equations by a single acceleration, which we call A. 2. The implication of a massless pulley is that tension on both sides of the pulley are the same. That is, the tension 3 equals the tension 4 in our diagram. The argument is that since the pulley has no mass, it also has no moment of inertia, which is a measure of its resistance to rotation. Since there's no resistance to rotation, the torques do not have to offset each other to cause rotation. The torques are equal. And since these torques are generated by the tensions T3 and T4, which are the forces of the string or cord on the pulley, tensions T3 and T4 are the same. 3. The implication of a massless string is that the magnitude of the tension 1 equals the magnitude of tension 3. And on the other side of the pulley, the magnitude of tension 2 equals the magnitude of tension T4. The argument here is that since the string is massless, the self-weight of the string does not contribute to the tension of the string. In real systems, there is self-weight, and these tensions are not the same. 4. And finally, we use the last two implications to show that the magnitude of the tension T1 was equal to the magnitude of tension T2. The argument being that if the magnitude of T1 equals the magnitude of T3, and if the magnitude of T3 equals the magnitude of T4, and if the magnitude of T4 equals the magnitude of T2, then the magnitudes of T1 and T2 are also equal. We then use these results to reduce the number of unknowns in our system of two equations from 4 unknowns to 2 unknowns. In this video, we're going to solve the system of two equations with 2 unknowns and then examine our results and attempt to extract some more insight on the dynamics of the ideal Atwood machine. Now, there are any number of legitimate ways to solve this system of equations. For example, we could solve equation 1a for t, and then substitute our answer for t into equation 1b, and then solve for a, the acceleration of the masses. However, I'm going to use a technique whereby we add the equations together and then solve for the desired variable. This technique is useful when it is clear that one or more of the unknowns will cancel. Now, by multiplying equation 1a by -1 on both sides, we see that the left side of equation 1a contains a negative t, and the left side of equation 1b contains a positive t. By adding these equations together, the t's disappear, and we have a single equation which we can solve for a. Now, after doing this, we find that the acceleration of the masses is the ratio of the difference of the masses divided by the sum of the masses, all times g, which is the acceleration due to gravity near the Earth's surface. Now, does our answer make sense? Well, let's first check the units. The difference of the mass m1 minus m2 has units kilograms minus kilograms, which is simply kilograms. Similarly, the sum of the masses is kilograms plus kilograms, which is also kilograms. And the ratio of kilograms to kilograms cancels and is unitless. This is good because the constant g already has units of acceleration, which are meters per second, or sometimes said as meters per second squared. So we see that a, our acceleration, has units of acceleration, and this is what we desired. Now, let's check two special cases to see if our answer accords with our intuition of Pulley dynamics. In our first special case, let the masses be equal. That is, let m1 equal m2. In our equation for acceleration, the numerator goes to 0, which means that our acceleration is 0. And this means that our masses do not move. And if our masses are the same, we would expect them to exactly balance each other and not move. So this checks out. Now, on the lower right, let's check another special case. Let m1 be much larger than m2. That is, let m1 be 10 times or even 100 times larger than m2. In such a case, the difference of the masses as well as the sum of the masses are both approximately equal to m1. So we are left with m1 divided by m1, which cancels. This means that our acceleration, a, is equal to g. Now this is exactly what we would expect to find in a simple free fall experiment. The mass m1 would accelerate at the rate g. If mass 2 were small enough, it does not have an impact on the system, and so the m1 falls as if it were in free fall. So this checks out. Our solution for acceleration has the appropriate units, and it holds up against our intuition as to how we expect the system to behave in a few special cases. Now, let's find a result for the tension. To do this, we'll substitute our answer for the acceleration, a, into our equation 1a. In the second step, we simply add m1 times g to both sides of the equation. In the third step, we factor out a common factor of m1 times g. In the fourth step, we find a common denominator by rewriting 1 as the ratio of the sum of the masses. In the fifth step, we combine the fractions and cancel terms. Next, we rearrange our equation and find our answer, which is 2 times the product of the masses over the sum of the masses, all times the acceleration of gravity due near the Earth's surface, which we have captured as the letter g. Now, does our answer make sense? Well, let's check units. In the numerator of our first term, we have the product of two masses whose units are kilograms squared. In the denominator, we have the sum of two masses whose units are kilograms. Kilograms squared divided by kilograms reduced to kilograms. So our answer has units of mass times acceleration, or kg times meters per second. And this is exactly what we expect for a tension force. So units check. Now, let's check to see if our answer for t fits our intuition about the dynamics of the situation. Now, we know that m1 is given to be larger than m2. This would suggest that m1 accelerates in a downward direction and m2 accelerates in an upward direction. Now, let's take a closer look at the conditions necessary to make the masses move. The free body diagrams will help us here. Let's first look at mass m1. In order for a mass m1 to accelerate downwards, its weight, m1 times g, must be greater than the tension force of the string pulling it up. That is, in order for m1 to accelerate downwards, there must be a net force in that direction. This condition is only satisfied when the weight of m1 is greater than the tension of the string acting on it. And similarly, in order for m2 to have a net acceleration upwards, the tension T must be greater than the weight of m2, which of course is m2 times g. In equation format, we find that T must be simultaneously less than m1 times g and greater than m2 times g. So, we can now ask ourselves whether our answer for T satisfies these conditions. We'll look at each case separately. The approach we're going to take is to first assume that our conditions hold. Next, we'll reduce or manipulate our equations algebraically until we get a condition we know to be true. If this occurs, then we know we can reverse our algebraic manipulations to get our original equation, which we can now conclude is also true. To help us with the math, let's assume that m1 is much larger than m2. The double arrow sign means much larger than. Now, if m1 is much larger than m2, then the sum m1 plus m2 is approximately m1. Plugging this into our equation for t and then substituting this equation into our condition that t must be less than m1 times g for m1 to have a downward acceleration, we find that m1 would have to be greater than 2 times m2. But this is exactly what we assume to be true. So this condition is satisfied. Now we can reverse our algebra to get to the equation above it. That is, we now know that this middle equation, which I'll point to here, is also true. And we can reverse our algebra once again, and we now know that our initial conditions are also true. We can use the same approach for m2. T must be greater than m2 times g in order for m2 to accelerate up. Given the condition that m1 plus m2 is approximately m1, we reduce our initial equation to the equation 2 greater than 1. Since we know this is true, we can work backwards to get the second equation, and then backwards again to get our initial conditions, our original equation. And we can now conclude that our original equation, t is greater than m2 times g, is in fact true. Therefore, we see that our formula for the tension t is at least consistent with the conditions necessary for the masses to accelerate in the directions that experience tells us they do move. Further, we have confirmed that the tensions of t are the units of force. Our equation for t checks out. In our next and last video in this series, we'll take a look at a variety of different approaches to a solutions that appear in online videos and in various texts. We'll use these approaches to get a better understanding of how to use and interpret sign conventions, a topic that creates a great deal of confusion for the novice learner.